Hello. The main objective of the Black Hole Lab is to study the motion of a star orbiting a black hole of unknown mass, integrating observations, theory, and computational modeling. Furthermore, the lab aims to calculate the mass of the black hole and answer the question if it is possible the mass of the new black hole to be different from the mass of the original black hole. For the purposes of the third physics laboratory, I applied physics principles and created a computational model in order to analyze the motion of the star. Using the provided position data of the star data CSV file, the model calculates physical quantities relating to the motion, such as the momentum of the star and the net force acting on the star. Based on the gravitational law of attraction and using the results of the computational analysis, I estimated the mass of the black hole. The constructed model calculates many physical quantities of the star's motion, among them the velocity, the momentum, and the net force acting on the star. The mass of the object was calculated based on the gravitational law of attraction and using the computational model data. Furthermore, based on physics principles, it was determined that if the black hole is replaced by a new black hole, still placed at the same location, and the motion of the star remains unchanged, then the mass of the new black hole must be equal to the mass of the original black hole. The net force acting on a system and consequently the change of momentum of that system can be analyzed into a component that is parallel to the direction of the momentum and into a component perpendicular to the momentum. Remember that the direction of the momentum is the same as the direction of the velocity. If the parallel component of the net force acting on the system is non-zero, then the speed of the system is changing. If the perpendicular component of the net force acting on the system is non-zero, then the direction of the system's momentum is changing. You can use geometry to calculate the rate at which the direction of momentum changes. Finally, we have the shown equation for the perpendicular component of the net force acting on the system. A star is orbiting a black hole of unknown mass, and the net force acting on the star is due solely to the gravitational force of the black hole. In order to find the mass of the black hole, we need the magnitude of the gravitational force for a specific distance between the black hole and the star and the distance. The computational model can provide us with the required data. The range of the visualization window was set in relation to the astronomical unit, which is roughly the average distance from Earth to the Sun, and it was set big enough so that it displays the whole motion of the star as well as the vectors representing the gravitational force. I specified the time interval between the sequential imported data points to be 86,400 seconds, which is equal to 1 day length. Using the momentum principle, I calculated the net force acting on the star as well as the parallel and the perpendicular component of it. Since the black hole is considered to be at the beginning of the coordinate system, the distance between the star and the black hole is equal to the magnitude of the star's position vector. I chose to output specific model predictions to a CSV file. The chosen output predictions refer to time in seconds, time in days, the magnitude of the net force acting on the star and its components, as well as the distance between the star and the black hole. Here is the model when it runs. As we can see, as the star approaches the black hole, its speed increases and vice versa. The output of the computational model is as shown. Selecting any pair of the net force acting on the star and the corresponding rates between the star and the black hole, we find the mass of the black hole. The result is the same no matter which pair we select. Let's suppose the first black hole is replaced by a new black hole, still placed at the same location, and the motion of the star remains unchanged. Since the motion of the star remains unchanged, the parallel component of the star's velocity remains unchanged, and the parallel component of the net force acting is the same in both cases. Since the motion of the star remains unchanged, the trajectory and the velocity of the star remains unchanged too, and the perpendicular components of the net force acting on the star is the same in both cases. Since their components are equal, the net forces will be equal too. The magnitude of the gravitational forces in the two cases are as shown. The distance between the black hole and the star is the same in both cases. Finally, we have that the mass of the black hole cannot be different in the second case. Thank you for your attention.